Welcome to this lesson on pressure changes in Aspen Plus. At the end of this lecture, we hope to be able to simulate the different types of pressure changing devices Aspen Plus and see how they work and how they can be integrated into processes. There are different types of pressure changes. Sometimes in a process plant, you might require some stream at a certain pressure or an elevated pressure. You might want to drop the pressure in the stream as well, especially for certain processes that require high pressures, like certain reactions and mass transfer operations that require high pressures. You need pressure changing devices to change the pressure of the stream to the desired pressure. Pressure can also be used to condense or for flash purposes. Is by increasing the pressure or reducing the pressure in the stream, we're able to liquefy or condense one material or vaporize it for that purpose. So there are a few of these. We have pumps, which is mainly mostly for liquids. Compressors are usually used for vapor phase compression. Uh, there are valves, pipe, pipings, right? They pipe systems where we tend to lose some of our pressure due to friction. We have turbines as well that decrease the pressure. So when you go into the Aspen model palette, the pressure changes are located on the model palette. You have the pumps, compressors, the valves, the pipes, and some of them represent the same function, just in a different convention. For instance, the compressor block is also used for the same purpose as the turbine. It just depends on what you select and the input and output for your stream. And so when it comes to pumps, we work with it if we know the pump efficiency and discharge pressure we desire. For this problem, we are going to use three components, mainly water, need oxygen, and then nitrogen simulation. For our method, let's use Frank Robinson. And we go to our simulation environment. So our first problem is pumping. To come to the pressure changes tab, add a pump. For assume water is pumped in these conditions, 4,000 kilograms. There are for material stream, and we want to pump this amount of water from a pressure of 1 bar to 20 bar. We have the efficiency, so we go straight to our pump block. We choose to specify the discharge pressure. That should be 20 bar, and the pressure to 20 bar. Our pump efficiency is 80%. And with that specified, we can run a simulation. Then when we go to the results, we can see the fluid power required and the brake power required. based on efficiency. There's the amount of power being drawn from the mains and the amount, the work the pump does on the fluid. It's because of the inefficiencies, we do not get a total conversion of the energy we put in, right? The outlet pressure, the pressure changes there, the outlet pressure. So we have all that fine. We can also look at our streams and see that we just have water, right? But the pressure moves from 1 bar to 20 bar. The next thing is to add a pipeline, a pipe to our simulation. Final pressure if the water is pumped through a 4-inch Shadow 40 pipe, which is 1 kilometer long, horizontal. So there is pipe here. And this is, if you have a single pipe, right, you choose pipe. If it's multiple pipes or a pipe network or a pipeline, you choose the pipeline. So right, you connect this outlet to our product. So we go to our pipe specifications, the length of the pipe, which is 1 kilometer. And now we choose to use the pipe shadows, right? And choose carbon steel. The shadow is 40 according to the problem. And the nominal diameter is 4 inches. Based on that, we can run our simulation. We have a warning that this is because we specify the two-phase. Can run our problem once more and you should have the results available. So we're able to see the pressure drop due to frictional losses. And if we look at the pipe is horizontal, so of course we don't have elevational pressure drop due to elevation. If we look at the duty, it's calculating a duty for us. That means it's operating isothermally. If we go back to our pipe and go to the thermal specification, you can see it's constant temperature. We can choose to run it adiabatically. So we see that there is a change in the temperature. Right. So that's it for pumps and pipes in Aspen Plus. For next, we are going to look at compressors and let's read out these. So compressors are used to increase the pressure of gases. So, and they are similar to pumps. They have in that they specifying the discharge pressure and the efficiency is all it takes for a simple compressor. We have multi-stage compressors, right? And if you've taken a thermodynamics class, engineering thermodynamics class, you're familiar with some of the terms here for compression. What it means to compress isentropically, polytropically, and isothermally. Right? And the effects on the adiabatic constant. Right. So this is the work estimated for compression, how the work is. And due to the rise in temperature associated with compression, which leads to more work, an increase in the compressor work for in compression. There are multi-stage compressors that are used to curb this, right, by compressing in stages when the pressure ratio the desired pressure ratio is high. Uh, for instance, if you're pumping something from 1 to 40 bar or 2 to 80 bars or a large range in inlet and outlet pressure, where you find that there are multi-stage compressors used to that effect to reduce the work by keeping the temperature constant. They achieve this by cooling, removing the heat associated with compression for every a single stage. Right? So we will solve a problem similarly. So we go back to our components. Air is a component. Okay, we are not going to use oxygen and nitrogen. We use air. And if we come back to our simulation, we add a compressor. Still, room temperature, 1 bar, mass flow rate of 12,000 kilograms per hour. Just type, and you go to our compressor block specification, choose polytropic. We specify a discharge pressure and the efficiency is 0.72. If that's done, we should be able to run the simulation. When we go back, you can view the results. So we see the energy required. We need 2,000 kilowatts or about 2.2 megawatts to achieve this outlet pressure of 20 bars. You can see the rise in the temperature. And this rise leads to more work for the compressor because it has to work against a hot expanding gas to bring it to 20 bar. It struggles more because of the rise in temperature. So we can use a multi-stage compressor with interstage cooling to achieve this. We'll delete the single compressor and reconnect our stream. Where, as the problem indicated, we are using three-stage compressor. Same calculation method. Then we specify the discharge pressure, 20 bar. We choose the equal pressure ratio for the optimal operating condition for the minimum work in a compressor occurs at an equal pressure ratio. And if we go to the cooler specifications, remember it's multi-stage compression with interstage cooling. So we remove the heat generated to keep the temperature constant. Right. So we're going to specify the outlet temperature and we're going to maintain it at the inlet point at 25 degrees Celsius. Then we can run a simulation. And once we do that, we see that the total work has dropped from 2.2 megawatts to 1.4 megawatts. Right. And this is the best configuration in which you can run it. You can play around this. You can choose to cool it, but not cool it to all the way to the inlet point and see that in that case, the duty rises because of that small increase in temperature we allowed. Okay, we can go back and run it without any cooling, right? By specifying a duty of 0. We choose not to cool anything. So we run it like the first case. And by doing that, we see that we are saying the same work or duty. We have to supply 2.25 megawatts of energy, similar to the single stage compressor. So the cooling there is important. There's the point of the multi-stage compression. Right? And the lowest achieved is still when we cool, right? We maintain the temperature at the inlet by removing the heat. So the duty is calculated for us. How much heat you have to remove for this process to occur. So that's it for pressure changes in Aspen. Plus, there are additional problems in the material, more challenging ones for training yourself or flexing your muscles. So if you look at this and if you want to run it in a different fashion, of course, if this was a turbine, then our inlet stream would have a higher pressure than the discharge. So here, the pressure specified here, the discharge pressure will actually be lower than what is coming in from here. And that's how Aspen recognizes that the block is being run in turbine mode. For a single stage compressor, there is a specification, right, as to whether you desire to run it as a turbine or a compressor. Right. So that brings us to the end of this lesson on pressure changes in Aspen Plus and the first part of our series on using Aspen Plus software. Hopefully in the future we will be back with more on more specific or different things in Aspen Plus. As you said earlier, the software is broad and very dynamic. And it can be used for so many things. So until then, goodbye.